Ryan is with Waukesha Engin, and he has the North American Sales Manager specializing in educating customers on the details and benefits of the Waukesha product line, also serving as the point of contact for many key accounts within the organization. Ryan has been with Waukesha business for 15 years in a variety of technical and commercial roles, spanning engine performance, controls, product management, marketing services, and new engine sales. Ryan has a BS and MS in mechanical engineering from the University of Wisconsin-Madison and an MBA from the University of Chicago. Ryan is also active in the GPSA as a board member and vice president. So please join me in welcoming Ryan.
Clicker. While you're doing that, I'll do my thing. Here we go. Smile, everybody. We're social media these days, right? It's blurry.
Proof you were here now, too, right?
Well, my boss is here. I think he knows. So showed up on time and all that stuff. Yep, that's a good idea. Sweet.
All right.
Awesome. So before I launch in, thanks, Drew, for the introduction, and thanks. Oops, I need to talk in the mic. Should I just hold it?
Does that need to be turned on, Mike? Or
He's got it. Yeah, he's already recorded my conversations. So, okay. Everyone can hear me okay? Is it on? Did you turn it off on me?
I turned it off. Yeah, hold it.
All right, we're good. Let's try that again. Much better. Okay. So, I always wanted to speak at one of these, so thank you very much for the privilege and honor. Hopefully it's not too boring. It helps that I'm first, so you guys can fall asleep in somebody else's presentation. Just a real quick plug. Drew kind of did a soft launch on it. As you mentioned, I'm the third vice president, whatever that means, of GPSA National. So if you're active and you're a supplier to the industry, certainly would put a plug in for the GPSA National group. I'll be passing some of these around. I've done a ton of great networking as part of that organization. Got to meet a lot of people, including the aerial boss, Mr. David Bardeen, and so on. So it's really been great for me. There's a lot of great benefits, including discounted to admission to the GPA convention that Drew mentioned. And if you like GPA type stuff, I think that convention is really a great experience. It's one of the best events of the year, if not the. So that aside, so my name is Ryan Verditsky. I think I'll skip the intro since Drew did a good job on it. What I'm going to talk about today is specifically related to emissions in the industry, where we've been, where we're going, and how maybe this may change thinking and behaviors of midstream companies, upstream companies, in terms of thinking about things like carbon emissions above and beyond just the regular permitting emissions. So hopefully I won't get too nerdy on all this stuff, and I'll connect. So quick plug for the company I work for, Waukesha Engin. We make engines that go into natural gas compression packages and also for power gen purposes. So we are owned by a company called INNIO, private equity backed, used to be owned by GE. From 2011 to 2018, GE had some issues with their balance sheets and had to find some things in the house to sell, and we were one of those things that they could do. So I've actually made money for GE, one of the few acquisitions that they had where they sold it for more than they paid for it, so good on us. Our sister company is Jenbacher. They make a bunch of high-efficiency power generation engines, so put one engine company together with the other. We all make connecting rods and crankshafts and so on. We just serve very different markets. So if you're in the market for high-efficiency power generation, hit me up and I'll kick you over to one of my Jenbacher colleagues. So quick little plug on the different models. Our smallest engine is a VGF. Been around for over 3 decades, 1,800 RPM. Little guy, relatively speaking. I mean, these are pretty big engines when it's all said and done. VHP is the bread and butter, 1,200 RPM engine, been around since 1967. And that's, 3/4 of what we sell typically. Very well known, and I'll talk a little bit more specifics about VHP a little bit later. And then the 275 is our big Boomba. That's a 1,000 RPM engine and gets up to 5,000 horse. This isn't a product presentation, but you know, I'm a sales guy, so you at least have to get over the basics, right? So if anyone has the fortune or misfortune of investing in oil and gas companies over the last 5 years, you can understand why I don't have much hair left. I did the same, thinking, hey, oil is going to go from 45 to 85. It did, but a lot of the stocks didn't really snap up in a similar manner. And part of what's going on, at least from my perspective, is that there's a lot of retail investors that are looking after more green companies, more sustainable companies. You know, obviously there was more things going on. You know, you need to spend within your cash flow, and your debt to EBITDA has to be so and so. But a lot of what's depressing, you know, at least the stock price of a lot of these different companies isn't that they're not cash flowing necessarily. It's that people don't know where they're going to be in 5 or 10 or 15 or 20 years. And so a lot of companies are out there trying to show, hey, oil and gas will sustain, will survive this green initiative. You need oil and gas to sort of provide the base level of heating and electricity generation and so on. So when the sun's not shining and the wind's not blowing, you have us. And especially on the gas side, you know, there's a lot to be said for the cleanliness and sort of bridge technology and all that other kind of stuff. So what's happening, though, is that there's more and more pressure above and beyond that sort of, I guess, value proposition to say, okay, well, that's great, but what are you really doing to minimize your emissions? Not just your NOAQS and your VOCs and your carbon monoxides, but your carbon footprint, your CO2, your CO2e. So I know that I parked right next to a Williams truck today, so I know somebody is here from Williams. You know, they've been very much in the forefront of, you know, hey, we're going to get to a net zero by 2050, and this is how we're going to do it. You can see sort of in the lower right, the sort of plan there. And the mix is some operational excellence, I guess. Let's go through our compressor stations. If we have old iron, we're going to switch it out for newer, lower emitting iron. But there's also other pieces to it. RNG is a big thing, renewable natural gas. So something I started my career at Waukesha with, and you know, some solar and everything else. So this presentation isn't going to talk about solar or RNG or anything. It's really focused on what you can do to at least consider different options for, you know, sort of minimizing your carbon footprint while still doing what you do best, which is moving gas, right? So this could get really boring really quickly, and I'm going to try not to get there. So this is a map of non-attainment zones. Hopefully you all have heard of non-attainment zones. Basically, if you're in a non-attainment zone, which is everything that's shaded, I guess I got a pointer on this bad boy, don't I? Laser. Yeah, you can see in the left side, 3 degrees, and I don't know how to work a pointer. So you can see on the left side, this is the non-attainment areas, anything that's shaded in as of 2008. Okay, so you get areas like California and their famous smog issues, right? And in the Northeast, obviously, there's a lot of activity there. That's where you have issues with ground level ozone and so on. Those are the areas where you have tighter permit limits for NOAQS and VOCs and such. So right around, I'd say, the 2015 timeframe, they were talking about, you know, sort of revisiting these zones, checking the meters, and seeing if the areas that were in non-attainment still are, and if there's some new areas that maybe should be considered. And this was, on the right side, the view of what people thought might happen depending on where the new administration was going to set their targets at, whether it was 65 or 70 parts per billion. It was previously 75. This is ground level ozone. So you can see that if it would have gone to 65 and the weather would have done what some people thought it would have, that you would go from not a lot to potentially a lot of areas, especially in the oil and gas zones. Oklahoma, Wyoming, Colorado, more, even West Virginia, right? Right now, West Virginia doesn't really have any non-attainment zones, at least as far as I could tell. So it could have a really big impact on our industry, right? Well, what ended up happening was not much changed. I mean, you know, you go back and forth between the two, it looks almost exactly the same. You know, there's a couple of differences. San Antonio popped up, but it was sort of I'd say a false alarm, right? But the writing is on the wall. We've seen what's happened with new administrations and some of the, I guess, talking points that have come in with, you know, emissions and so on, and we'll talk about a little bit more later. You know, this, if they keep ratcheting down just the NOAQS piece of it, that could have a real material effect on how we do business, right? So had a pretty spirited debate with some customers last night about emissions and what role they're going to play in sort of our operations going forward. And I think the problem that everyone has is recency bias. Okay, everyone says, well, 0.5 gram NOx, that's going to be totally fine for my application. It's been that way for 5-10 years. Well, 20 years ago, we didn't really have any NOx emissions, right? I mean, we could permit a 2-gram engine, no problem, pretty much anywhere. And when 2008 happened and non-attainment zones and the Barnett blew up, that's when all of a sudden this was a thing. And from our side, we had to do a lot of product development and really focus on, not just how much power do you make and, in what conditions, but also what your emissions are. So the point of here is, instead of going up and to the right like everyone wants their business forecast to go, we're going down and to the right, and it's not going back up, it's just going to keep going down. So when I'm talking to customers and I'm talking about our products, I'm saying you can't think about right now, you can't think about 5 years from now. If you expect to have this asset for 10, 20 years, you need to have a growth plan that says, okay, if it goes to 1/4 gram or 1/10 of a gram, what are you going to do? Okay? So that's the point of this slide. And I'm not going to explain all the different things, but the point is that the big fat line is sort of the national standard for gas engines. Everything else is other equipment, on highway, off highway, European standards, and so on, and they're all going down. Okay. Colorado, of course, has made some news lately. I realize we're in Appalachia right now, but what happens in Colorado gets copied elsewhere, just like what happens in California gets copied. So it's kind of a cautionary tale of what could happen. Again, I'm not going to get into specifics on this, but there's 2 major points from this slide. Point 1, they're going after grandfathered engines, okay? And that's sort of the sacred cow of the industry is I got my old Cooper Integral and it's gonna go forever and it's great and well, if you need your Cooper to go 0.5 gram or 0.15 grams, you're gonna have a bad time, right? So, and so that's where, we come in, and Ariel comes in and they say, okay, well, you need to move gas, let's talk, maybe we can swap you out or whatever. So it's that everyone thinks, well, I bought it at this time and this is all I have to care about. That's not gonna be the reality going forward. At least that's not from where I'm seeing, okay? So that's point 1. Point 2 is everyone wants to electrify in Colorado, or at least the air quality management. And that's great, but it costs a lot, and I know NFG's got some really good numbers on what it costs to run high voltage power to a site. It's $1 to $3 million a mile, at least, depending on where you're at. That is a real material cost, that has a real material impact to schedules, and it has a real impact on the operating costs, because electricity costs money, much more than the natural gas powered. So something to consider. The other piece is that the electric operators, or your We Energies and your Encores and so on, they basically pushed back and said, we can't build power fast enough. We don't have the capacity. So, cut it out. You need to have more solutions than just electrify everything. So New Mexico is doing something very similar. The thing that I think, this is a proposed rule, and don't get baffled by all the numbers on it. The point is they're going after existing engines in their proposals, and they're also ratcheting down very hard on volatile organic compounds. I mean, 5-10 years ago, it was all about NOx, NOx, NOx. Now, everyone's ratcheted down their NOx, and suddenly they're having issues with VOCs. And that's not just an engine issue, that's a compressor issue, that's a pneumatic issue. VOCs, more and more, we're seeing are the real limit to how big you can build a site out. And this is an aggressive target. People are either going to be driven to run pipeline gas to their compressors so they can knock down the heavies that are coming out of their exhaust and causing VOCs, or they're going to electrify, or maybe they'll buy some rich burns, which is why I'm here. So, okay, everyone still with me? Yeah. All right. So, kind of shifting focus a little bit from the permitting side, the NOx and the VOCs and the carbon monoxides, to the GHG side, greenhouse gases. And really what the true mark of a greenhouse gas is in our industry today is a combination of CO2, carbon dioxide, and methane, okay? And methane has definitely been a focus of the industry, Quad O, I don't know specifics on it because I'm an engine guy and not, a balance of plant guy. But the bottom line is right now everyone's going after leaks and pneumatics and blowdowns and all that sort of thing. And nobody's paying attention to what's coming out of the stack, out of the engine stack, right? And that's fine. I'm not calling up people and saying, hey, look at us, but it's going to happen. And so people need to plan for it. And when you start peeling back the onion and you see the portion of an overall site emission sort of footprint and the portion that the engine makes, it can have a big impact on the overall site emissions, okay? And when you see people with satellite cameras looking at methane emissions, they're gonna start saying, well, what's coming out of there, okay? So big piece of this slide is the multiplier of methane. So if you have one methane molecule and one CO2 molecule, the CO2 is gonna be 1 gram, call it. Methane will be 25 gram of CO2 equivalent because it has a much bigger impact on the greenhouse effect than just CO2. And that's just where we're sitting today. There is talk that this multiplier will go from 25 to 84. There's talk that people may start taxing methane emissions. So again, people are gonna start thinking much more closer on this. And I have some more slides to explain this. Hopefully I get to them if I can keep moving. So I mentioned this before, so I'm talking in front of my slides a little bit, but again, right now the focus on EPA is almost everything but the engine. The assumption is that the engine, when it combusts, is similar to a turbine. Turbine has very low methane emissions, very complete combustion. If you start looking just at nameplates from a Waukesha or a Caterpillar and what the real methane emissions coming out of the engine are, as we tell you when you're looking at a data sheet, it's quite a bit higher. And I, again, talked in front. So especially when you look at the lean burn side of things, you know, it's in some cases 500 times as high as what the EPA currently estimates. So if you are what's considered a major facility and you have, you know, I think it's along the lines of maybe 10 or 20,000 horse, I don't know off the top of my head, you have to report your greenhouse gas emissions to the EPA. But what they tell you is grab your fuel meter, tell me how much fuel you burned this year, and put it into this equation, and that's what your CO2 is. And they're not looking at the methane emissions, they're just looking at how much fuel you're burning. They're assuming that combustion's almost perfect. Well, as you can see, that's not the case, okay? So if you look at a typical lean burn package, and I'll talk a little bit about lean burn versus rich burn later. If you look at a typical lean burn package, which is the vast majority of gas-driven compression today, 2/3 of the overall CO2e come from just combustion CO2, and 1/3 is coming from methane. Because again, methane's a 25x multiplier compared to CO2. Okay, and I'm boring myself right now. Okay, so if you cut that 1/3 out and split it up, so you take the 1/3 that's coming from methane and then you break it out into where that methane is coming from, half of it is coming from the lean burn exhaust, typically. Overgeneralizing, but it's a pretty good estimate. And this isn't like, oh, this is my old 7042 GL that I bought back in '98, right? We're using a brand new 3600 for this calculation, okay? 4 or 5 grams of NOx, 4 or 5 grams of methane if you're burning clean gas, okay? That's a lot. So they're missing a lot. It's a big deal. Now, if you go rich burn, and I'll be in the back corner if you want to take orders later. If you buy a rich burn, almost all that goes away. And I'll pick that back up again later. So a lot of options in the industry about how you move gas from point A to point B. I'd say the 3 major options that people are looking at are a gas-powered reciprocating engine, an electric motor, or a gas turbine, okay? Reciprocating engine, been around for a long time. A lot of people know how to work on them. You know, very forgiving, very flexible. You can run, you know, 3/4 speed, half torque, so you can really get anywhere from 37% of rated power all the way on up. You never know what your flows are gonna be. Sometimes people need gas, sometimes they don't. Reciprocating engine does a really good job, paired with a reciprocating compressor, of course, of sort of meeting your uncertain needs, okay? Problem with reciprocating engines is they got a lot of parts. You got a spark plug, and you got a piston, and you got a cylinder head. And sometimes that stuff breaks, okay? It's machinery, it's running 24/7, 365. Maybe somebody didn't do a valve adjustment quite right on their last PM, and you know, now you're fixing parts, okay? But the parts are generally plentiful, they're cheap, so it's a good package for what you need it for. Electric motor, no site-specific emissions. The electric motor itself is pretty inexpensive, but the infrastructure to put it in, the VFDs, the power lines, all that stuff is not. The power costs can be very high depending on what you're paying for gas versus electricity. And if something goes bad, you know, you're not just back up and running. You might be pulling the whole unit and putting in a new one, and lead times can be an issue and all other stuff. Gas turbines, great for big 2 BCF pipelines, blow a lot of gas for a small amount of power, or for a small amount of cost up front. But when you start having to run off peak, that's when you start having potential issues, okay? They don't do a great job if you want to run them quarter load or half load or something like that, like a Recip would. So, talked about this a few times before. Electricity can cost a lot of money, especially when you're chewing it off in 20,000 horsepower or 15 meg chunks, right? And gas, in case anybody hasn't been paying attention, is pretty cheap, and it has been cheap for some time. So if you're a gas company and you're not paying the retail rate versus paying maybe a wholesale rate of electricity, but you're still paying somebody other than yourself to produce it, this spread can mean a big deal. So essentially what this table is a sort of matrix of if you're paying $1 for a million BTU of gas versus 5 cents all-in kilowatt electric on a 20,000 horse station, you can save $5 million a year on your fuel bill. If you're only paying, or if you're paying $5 and you're only paying 5 cents, you're only saving $500,000. All right, I get it, that's not that much. But I think reality is people are probably paying around 10 cents, give or take, when you look at the true cost, not just your base rate, when you look at demand charges and all the other stuff, and you're probably paying between $1 and $3. So you're saving maybe $10 million a year on a 20,000 horse station by using a gas driver versus an electric driver. That's a lot of parts you can buy. That's a lot of technicians you can hire. That's a lot of money. Now, why are people doing a lot of electricity? Because they can pass that cost to the producer. And the producers are eventually going to figure it out. Everyone's tightening their belts. You know, if they're leaving $10 million a year on the table, that, you know, I can't, as somebody who considers himself a half economist, I can't imagine this continuing to go on without somebody saying, okay, this is a way we could save money. Maybe I'm an optimist. I work for Waukesha after all. So, other piece that would maybe, you know, is my plea to look more at recips in all applications, not just to typical gathering apps and so on, is fuel consumption, which recips typically have an advantage on, and flexibility, which we definitely have an advantage on, may matter more and more in the future when you see more forms of gas coming online and more intermittent forms of gas. Sun's up, sun's down, you know, wind's blowing, wind's not. So the demand for gas may fluctuate accordingly. So you know, maybe it's not going to be your big, you know, 2 BCF pipeline running to the Northeast. Maybe that's just going to be stuffed because, you know, we're capacity constrained. But there's going to be other areas where the past will not predict your future. Because, you know, in the past, maybe it was stuffed all the time, and in the future, maybe it's only stuffed half the time. So, you know, my ask isn't, and again, I'm getting ahead of my slides, my ask isn't to say, okay, go build a 70,000 horse recip station. It's maybe build a 60,000 horse turbine station, then put a 10,000 horse recip station next to it to handle the ups and downs. And some people are doing that right now. Other piece of this is, you know, I talked about the potential methane changes, whether the multiplier goes from 25 to 84 going forward. There could be a methane tax. There could be a carbon tax. All those things point to caring more and more about fuel consumption. When I started working at Waukesha, I thought our 40% engines were just the bee's knees, they're the best thing ever. And then we looked over at the VHP and it was running at 30%, and I was like, oh, like, you know, you kind of, oh, this isn't really that great. And then people say, well, nobody cares about fuel consumption in the industry. You know, you just pass it on to the next person. I think that's going to change, because when you start getting carbon taxed, as Alberta's already getting, you know, then you start to pay attention real quick, you know, when you're getting hit in the pocketbook. So talked about the ESG targets and the pressure to reduce your carbon emissions to become net zero. All those things are going to play into why flexibility and fuel consumption will matter more. So my hatchet job against turbines, since I don't think anyone from solar is here. This is essentially a turbine curve. So what you can see up to the right is the output power versus the heat rate, and you can see inlet air temperature versus heat rate and power, okay? So turbines need density at the inlet to make power on the back end, okay? And the higher you get in elevation or the hotter it gets, the less dense the air is, the harder that turbine has to work to make power, okay? And when you see one of these curves, it looks good. You know, a Titan 130 is an awesome machine, but it's got a lot of assumptions. You know, 59 degrees Fahrenheit and 0 feet above sea level. Nobody permits there, right? You know, people are at 100 Fahrenheit and 3,000 feet above sea level or 5,000 feet above sea level. And when you start doing that, you either need to run an air conditioner at the inlet to get the density you need to make the power you want, which has a cost and associated with it, or you're going to take a power loss and you're going to take a heat rate loss as well. As you get down that power chain into the Taurus and, you know, the Centaurs and stuff, those heat rates start looking pretty lousy. Okay, you know, our engines typically run 6,500 to 7,000. Lower is better for those that don't know. These are up in the 8,500 range. So again, fuel consumption will matter. So does power output. And then other people will say, well, hey, I can't beat a turbine at, you know, 9 ppm at 15% O2. Well, you can. That's about 0.15 gram NAAQS. That's what our rich burns do, okay? Again, throwing a little sales on here. So you contrast that with what a typical Waukesha can do. And this is, you know, same with a Caterpillar or any other engine manufacturer. The sort of fall off curve of fuel consumption and sort of torque turn down and everything else is much more forgiving, okay? Your fuel consumption actually gets better as you slow down your engine, okay? So for people that are looking for flexible futures and carbon reduction and all that other kind of stuff, Recips are a really good fit for that. And as I mentioned before, the NOx of an engine is very competitive, at least with a rich burn engine, with the best turbines out there. So here's an example I got from one of my customers. I anonymized it because, you know, it's data and you don't want to share that with other people. But this is some stations that they are looking at on a big pipeline, okay? So station 1, the design limit, what they think the max that they're going to need, or at least what they can permit for, is 70,000 horse. Station 2, 55, station 3, 35, okay? And for each of those stations, they have different scenarios. Are they going, you know, it's a bidirectional station, so are you going north, are you going south, is it winter, is it summer? So I broke those down into different scenarios. So each scenario should have one sort of point where it's running at peak, right? You can see that with station 1, scenario 1. It needs 70,000 horsepower in this one spot. But for scenario 2 and 3, in some cases it needs nothing, it's just blow through, or it's off peak. So that customer is looking at 2 to 3 turbines per station. And my question is, okay, that's great, but what happens when you're running, you know, station 2 and scenario 3, you need 38% of your power. Can you just run one turbine? Are you gonna run one turbine and one sort of off? And how much fuel are you gonna burn? Because typically when you're running off peak, you have to recirculate. Well, recirculating just means you're gonna take the gas from here and you're just gonna run it right back into the intake. It's just wasting gas. And in a low carbon future, I'd rather tackle that problem than just build some solar to cover that up. Okay, it's just not a cost-effective way of doing things. So again, back to the plea of don't just build turbines all the time. Think about a more eclectic future where you have some recips here and you have some turbines here, and maybe you're next to a power station here and you got cheap electricity, but it's going to be takes a little bit of everything to kind of win in the future. So where do we go from here? So again, I just kind of mentioned it a little bit. This is really all about having different tools in your tool belt, okay? Different things are going to call, or different scenarios are going to call for a better set of tools, right? I'm not going to, well, sometimes I use my hammer for everything, but I'm not going to, you know, hammer in a screw, right? So what you can see in the lower right is a map of sort of the carbon intensity of the US as, you know, sort of broken out by different grid regions, I guess. And if you see lighter colors, you're talking about a less carbon intense grid. So big surprise, California, not that carbon intense, a lot of solar, a lot of wind. And again, this is sort of marginal carbon production. This isn't counting like what it takes to build the turbine and a solar panel and so on. So in those situations where, you know, if somebody's going after a low carbon world, I guess, running electricity makes some sense, okay? But if you're in North Dakota, if you're in Wisconsin, where there's still a lot of legacy coal, obviously there's a lot of legacy coal around here, and you're gonna say, I'm green, I'm running my electricity, I'm going to say, no, you're not, because you're running coal basically to power your compressor. I have natural gas, and this is a lot cleaner. So, and I'm taking the gas from the pipeline right here, and I'm just running it right here. The actual cost to get the fuel to my compressor is almost nothing, okay? So to my point is, if people really care about being green, they need to look at what their true carbon footprint is, wheel to, or womb to tomb, so to speak. What does it cost to run those power lines, to mow down those trees, to, get to my station? And, what does it cost to actually, or what's actually powering that station when it's actually electrified? The other piece is the overall grid for natural gas when you look at NAAQS is the overall grid for the US when you look at NAAQS is very good. But there are areas where a Recip can do better. So typical Recip nowadays is 0.15 gram NAAQS, 0.3 gram NAAQS, maybe 0.5. The lower 48 range is 0.06, which again is one of the coasts, on up to 0.55, which I can't remember. That might be like North Dakota or something. So again, when you're looking at the overall environmental health, running on natural gas makes a lot of sense in certain areas. Okay. About 2/3 of the way through, and it's only getting worse. Okay, so I talked a little bit before about lean burn versus rich burn. Okay, so and may have gotten past my skis a little bit, as I've known to do. So essentially, what a lean burn engine is, I'd say, is similar to a diesel. If you have a diesel in your car, you're jamming a lot of extra air in, and if you whip up a chemical equation up on the board and put CH4 for the methane molecule and some air, the perfect amount would be stoichiometry to get your equation to balance, your products and reactants. Let's go back to high school chemistry, right? On a lean burn, you double the amount of air in some cases. And you do that to keep your combustion temperatures low, okay? And why you want to keep combustion temperatures low is that engine stack out will get you lower NOx, it'll get you, other benefits in terms of emissions. But there's trade-offs to that. Right? And as we continue to ratchet down on emissions, the trade-offs are getting harder and harder to manage, okay? Rich burns, on the other hand, if you don't have a diesel in your car, or rental car, or whatever you came here in, more than likely you're running a rich burn. So it's stoichiometry, starts well, loads well, you got a catalytic converter, hopefully it didn't get stolen out, this morning. I've had that happen to me. And that catalytic converter does a lot of the heavy aftertreatment lifting. And they've been around for 30 years. They're relatively inexpensive other than precious metal costs, which you have to deal with on lean burns anyways. Very well developed technology, simple to operate, very well accepted in the market. So I'm gonna skip over this, but point is that there's other benefits to rich burn versus lean burn in terms of forgiveness. If the wind changes, if the fuel changes, rich burn's gonna have a better chance of running through those sort of interruptions. So when it comes down to doing a sort of side-by-side state-of-the-art comparison of a lean burn versus a rich burn, when you look at some of the major hot-button emission items, VOCs, again, at the top of mind, a rich burn, when you add that three-way catalyst, is going to be 12% of what a lean burn is doing, okay? That's a big deal for people that are trying to permit, okay? You'll see that in the next presentation. That was a big driver behind the decision to go lean versus rich, was what that site permit looked like and what the driver was going to add to that site, okay? Formaldehyde, a big deal, huge advantage there. NOx, 50%. CO, no, we won't talk about CO right now. Maybe you're at a bit of a deficit, but methane's another piece, right? Again, we've hammered on methane through this whole presentation. Less than 10% on a rich burn versus a lean burn, okay? And particulate matter is another presentation for another time if you want me to really get nerdy, okay? Which I know you don't. Okay. SCR, okay, this is what a selective catalyst reduction system looks like, as written by the manufacturer of said selective catalyst reduction system, okay? If it looks like something from Back to the Future, it's because it kind of is, okay? So if you have AdBlue or DEF in your new diesel, they've done a good job with that, okay? It seems like it's a relatively seamless process, but when you're talking about a 20,000 horse station, people have described this as more complicated than just running the package itself, okay? And so if people keep going down the lean burn route and NOx emissions keep going down further and VOCs get tighter, this is what you're pushing yourself into. It's complicated. It requires shipments of urea on site at some periodic basis. It's got the same amount of catalyst, if not more, than a rich burn. It's a lot. And so far, the industry hasn't gone there and hasn't shown a willingness to, okay? VOCs, again, I can't emphasize this enough. VOCs are, in my opinion, the biggest sort of challenge from an emission perspective that the industry has faced in the last 5 years, okay? Because everyone's drilling for hotter and hotter fuel because they want the oil, and the gas that's coming out is of higher BTU content. They're getting higher BTU gas that's going through the engine, and they're getting this on the back end. So what these are light-off curves of different emissions constituents, your propanes, your butanes, your ethanes, and so on. Nobody really cares about the fact that it's hard right now to light off methane in an exhaust stream, but they sure care about the fact that it's hard to light off propane, because propane is considered a VOC, methane and ethane are not. By definition, VOCs are non-methane, non-ethane hydrocarbons. So I can't tell you how many customers I've talked to that say, I have to put 8 to 10 catalyst elements on the back of my lean burn to get it to pass emissions. I thought I would need 4. And that has a real material cost. On a 20,000 horse station, that could be $175,000 to $200,000 a year. Well, if you have to exchange the catalysts every year. If you can wash them, it'll be less. But that's how much catalyst people have on these sites, okay? Running Marcellus gas, all right? As you can see here, because rich burns run hotter, they have more complete combustion, you don't see the VOCs coming out of the exhaust like you would with a lean burn. So these 3 curves, okay, the top curve is a lean burn engine out. As you get more propane in your fuel stream, your VOCs go up, okay? The catalyst, the oxidation catalyst that is used is assuming a 50% reduction, so you can see that second curve is half of the first curve, but it keeps going up, right? And if you remember back to what New Mexico was talking about, 0.3 gram NOx, that means that you would have to have less than 5% propane in your fuel. And when you look at Permian gas, when you look at Bakken gas, when you look at Marcellus gas to a lesser extent, lots of people have 5, 10, sometimes 15% propane in their fuel. So you either have to treat it with a JT skid, or you have to buy a Waukesha. Because if you see on the bottom, the rich burn curve is pretty flat and it stays that way, okay? I can dance too, by the way. So, getting close to the end, this is a comparison of sort of the many drivers out in the industry today, and you can see the whatever color that is, blue or purple, I'm colorblind, that's the CO2 portion of what's coming out of the exhaust for an overall CO2 calculation. The red is the methane impact, okay? So I mentioned before, it's not unusual to see 4 grams coming out of the state-of-the-art lean burn today. And when you multiply that times 25, now you got 100. So if you have 500 grams per kilowatt hour of CO2, and then you have 4 grams per kilowatt hour of methane, now you're at 600. So now even though a rich burn may not be as perfectly efficient as the state-of-the-art lean burn, we're coming up, from the back like the tortoise and the hare because we're way better on methane emissions. So again, for people that are concerned about CO2e going forward, this is a very cost-effective path to go, okay? And we have some of our own products in there, so we're not just slamming the competition. I mean, we have lean burns too, right? And we're working on that. So one last slide. So I talked a little bit about permitting and site permitting, right? Everyone, if you've seen a station get built, if you've seen where companies have gone, especially in the Northeast, everyone wants to build, pads that have more wells, longer horizontals. Everything's coming to a more centralized gathering facility, bigger processing. I mean, people are doing BCF processing facilities in some areas. It's crazy, right? And they want big horsepower because of economies of scale, right? If I buy a 5,000 horse unit and lay 4 of them alongside, that's going to cost me less than if I did, 8 2,500 horse units, because there's more piping and there's more foundations and all that other kind of stuff. So bigger is better in that regard until it's not better, like Paul's presentation will show, okay? And so this is basically showing what a general permit limit would look like. So if somebody wants to build a 200 milliday station in Pennsylvania, if you want to do a general permit, a GPO5, these are your limits: 50 tons of VOCs, 10 tons of formaldehyde, and 100 tons of NOx and CO. What you can see on the right is what would happen if you built it with rich burn So you could build a 34,000 horse station with rich burn, and CO is what you're timing out on, so to speak. On the lean burn, it's 12,000 horse, almost 13, okay? And that's timing out on VOCs. Well, if you have rod packing VOCs or you have pneumatic VOCs that are on your permit, you can cut that by a quarter or a half or whatever. So now you're looking at a 6,000 horse station. That's not a very big station, right? Not a lot of other CO emitters out on site. Okay, and this assumes 6% propane in the fuel, which again is about Marcellus gas. So again, we think there's a real value to looking at rich burn engines more. You always knew there was going to be a little bit of a sales piece of this, right? It's not just emissions education or a way to catch up on your email. But yeah, we think there's a really compelling case for rich burn engines in the industry for permitting reasons, for CO2e emissions, for flexibility going forward, because it's a very uncertain future for our industry. And so that's kind of where I'm going to leave it, I guess. So if, I think I got about 5 minutes for questions maybe, or, yeah.
Can you give me just a quick difference between the rich and lean burn engine mechanically? What are you doing technology-wise to make one?
That's a really good question. So I'd say that the challenges on a rich burn versus a lean burn are very different. So lean burns typically have higher firing pressures. So you're looking at, can I design a power cylinder and a rotating assembly that, it's great when customers call you when you're up here, that can withstand higher firing pressures, right? The rich burn is all about heat. So you don't have that extra air going through the combustion chamber to have cooling effects. So we, on the Waukesha side, have to find ways to have materials that can withstand for 3 years of constant operation and have the cylinder head last in a 1,200 to 1,300 Fahrenheit environment, right?
Just stronger materials in general.
Yeah, it's more heat-tolerant materials. Now, on the actual combustion side, rich burn combustion is pretty simple. You screw a spark plug into your combustion chamber and you go, because you're not trying to light off this super lean mixture. Whereas increasingly with lean burns, you have a pre-chamber, you have an emission valve, you may have an injector. So it's more complicated and it's more maintenance potentially. But people out there have done a really good job of designing cylinder heads and pistons to last a long time in lean burns. So, any other questions? Crying uncle? Taking you back to school? Okay. Well, if you have any other questions, I'll be seated in the back corner with some of my colleagues. And again, we'll take orders. It's totally fine. So thanks for the attention, and thanks for the opportunity.